All right, let's just jump right in with a wild idea. What if time isn't actually fundamental? What if it's just a side effect, an illusion that's created by our 3D universe bumping up against a fourth spatial dimension? Today, we're going to dig into a radical new theory called the time force hypothesis. It proposes exactly that, and it just might solve some of the deepest puzzles in all of physics.
So to really get why this new theory is so important, we've got to look at some of the biggest unsolved mysteries out there. And the first one, it's something you feel every single second of your life, the arrow of time. I mean, the basic laws of physics, they work perfectly fine forwards or backwards in time. So why is our universe stuck on this one-way trip from the past to the future?
Okay, mystery number 2. We're zooming out from our daily lives to the entire cosmos. We've known for about a century now, right? The universe is expanding. Everything's flying away from everything else. But what's the engine? What's actually pushing it all apart? The Standard Model has some ideas, but this theory offers a totally different explanation.
And for our third puzzle, we're diving down to the teeny tiny quantum level. Why do all the fundamental particles have the exact specific masses they do? And why are those masses quantized? Why do they only come in these neat, tidy little packets of energy? Our best theory so far basically just shrugs and says, well, that's just how they are. It doesn't tell us why.
So you've got these 3 huge disconnected mysteries. But what if a single elegant idea could tie them all together? That is the absolutely massive ambition of the time force hypothesis. And it all starts by doing something unthinkable, throwing out the idea that time is even real to begin with.
Okay, so here's the core idea in a nutshell. The time force hypothesis, we'll call it TFH, says that our universe, our entire 3D reality, is just trying to find its balance inside a bigger 4-dimensional space. And get this, the theory claims that this one single process, this settling down, this search for equilibrium, is the engine behind everything. It creates what we think is time, it's what's pushing the cosmos apart, and it even decides the exact masses of particles, all from one simple principle. Yeah, I know. That sounds completely wild. So how could that even work? Well, the whole mechanism hinges on picturing our universe as a kind of membrane, or a brane, just floating around in a higher dimensional space. Let's try to visualize this. Think about it like this. Picture a perfectly flat, 2-dimensional sheet of paper. Now, imagine that sheet of paper existing in our 3D world, right? Well, TFH says our whole 3D universe is just like that sheet of paper. We are living on a 3D surface, but it's embedded inside a bigger 4-dimensional space that they call the bulk. And the crazy part is, we can't get off this surface. And this is where it gets really cool. This is how time supposedly appears out of nowhere. The theory says that energy from our 3D brain is constantly leaking out, just bleeding into that 4D bulk. And here's the key. That leak is a one-way street. Energy goes out, but it doesn't come back in. And that steady, unstoppable one-way flow of energy, that is what our brains interpret as the forward march of time. Now, the paper itself gets pretty technical, but the idea behind the jargon is just wow. What we see as the irreversible arrow of time is really just the shadow of a simple energy exchange happening in 4D. So the universe isn't really breaking any rules. We're just seeing this big balancing act from our limited 3D viewpoint as everything settles down. All right. So providing an origin for time is already a huge deal. But this is where the theory goes from interesting to potentially revolutionary. It claims it can explain where mass comes from, and not with quantum mechanics, but with pure, simple geometry. I mean, this is a total break from how we've thought about physics for a century. In standard quantum mechanics, quantization, the idea that things come in discrete packets, is just a fundamental rule. You just have to accept it. But TFH says, no, it's not a rule, it's a result. I love the analogy of a guitar string. You pluck it, and it can only vibrate at specific frequencies to make specific notes, right? The theory says particles are the same way. They are just the stable, in-tune, geometric shapes that can exist in this 4D space. And this chart just lays it all out perfectly. The Standard Model, it sees a particle, measures its mass, and writes that number down in the equations. TFH says, hold on, I can predict that number from scratch just by figuring out the stable geometry. It's trying to answer the why that quantum mechanics has always had to sidestep. And this isn't some vague, hand-wavy prediction. This is where they really put their money where their mouth is. The theory makes an incredibly precise prediction with no fiddly knobs to tune. They call them free parameters. Based purely on the geometry of what should be the most stable fundamental vibration, TFH predicts a brand new particle with a mass of about 2.05 giga-electron volts. That number just pops right out of the mathematics.
Look, a wild theory is fun to talk about, but to be actual science, it has to be testable. More than that, it has to be falsifiable. It needs to make bold predictions that, if they turn out to be wrong, bring the whole thing crashing down. And that's exactly what TFH does. It practically begs to be proven wrong.
And that right there, that's the sign of a strong scientific theory. It's not trying to hide or make excuses. It lays out 4 totally separate, incredibly specific predictions in completely different areas of physics. If even one of them is wrong, the entire framework is toast. So, let's see what they are.
Okay, check this out. 4 ways to break the theory across 4 different fields. First, particle physics. They're going to look for that 2.05 GeV particle at the Large Hadron Collider. Second, atomic physics. They're looking for this impossibly tiny atomic noise, a little wobble that only the next generation of supersensitive detectors could ever spot. Third, cosmology, a really unique prediction for how the light from distant galaxies changes over time. The newest giant telescopes will hunt for that. And finally, astrophysics. They think there should be a weird little fuzziness in gravitational waves that our space-based detectors, like LISA, might be able to pick up.
And the scientists behind this are not messing around. They state it right there in the paper. A 5 sigma deviation, that's the gold standard for saying this is wrong in physics. In any one of those 4 tests, and the whole theory is refuted. Done. No going back and changing the parameters to make it fit. They've drawn a line in the sand. That's some serious confidence.
So what does this all mean? Why does this matter? Well, if this thing is right, it's not just a small step forward, it's a complete game changer. It would finally connect the world of the very big, cosmology, with the world of the very small, particle physics. It would give us a real, physical reason for why time only moves forward. It would totally redefine how we picture reality itself. And the best part? We don't have to wait 100 years to find out. The experiments that can prove or disprove it are either running now or coming online very, very soon.
Which leaves us with one last, kind of unsettling thought to chew on. This theory challenges our most fundamental experience of the universe, the feeling that time is passing. It says it's an illusion. If it turns out to be right, it really makes you wonder, doesn't it? What else about our reality, what other things we take for granted, are just shadows being cast from a higher dimensional world that we can't even begin to see?